Okay, welcome back, everybody. So today we are going to do a bit of a summary of what we've gone over so far, maybe introduce a couple of extra bits and bobs that will enrich your understanding of what's going on, or themes that are going to show up later in the course. We can work on seeing some of those phenomena in the univariate setting, and then understanding that will pay dividends later for our understanding when things get more complicated. Okay, so we had a request to go over Cauchy game in a little bit more detail. Okay, so the story looks like this, right? So we have some homotopy paths. This is the picture we keep seeing. I'm gonna not label everything in it. If you have a question of what something is, just let me know. And we have some paths coming together with multiplicity. Right. And these paths are part of a variety. It's really just the variety cut out by our homotopy equation. Living inside C2, which we really think of just as having x coordinates and having t coordinates. Newton-Puiseux says that this is, let's call this x1 of t, x2 of t, x3 of t. X2 of t, let's call this x star, really looks like x star plus the sum, going from 1 to infinity, of some aj's t to the j over w for sufficiently small p and some w in here. Last time I called it the winding number. Subtle distinction with the winding number. I'm going to call this the cycle number of this. Okay. Winding numbers are things relating paths and some points, specifically loops and points. Okay, you can talk about how many times the loop winds around something. It's very closely related to this story, but I don't want to talk about the winding number of a point. I want to talk about the cycle number of a point. Okay, and that's more consistent with the language in the literature. Okay, things that look like this, they aren't power series because we have fractional exponents. They're called Puiseux series. But of course, if we take s to be s to the w to be t, then we do get a power series.
So this w would be like the LCM, right? When we clear the denominators.
So this is not w sub j, this is w. This is already
cleared.
A cleared thing. Yes.
Okay.
So now if you talk about Puiseux series in general, then yeah, you can only have finitely many different types of denominators. Equivalently, you can only have one because you can take the GCD.
Right.
Yes. It is. Okay. Great. So this ends up looking like that. So that's power series. In other words, this is analytic. So there's a map, so it's holomorphic. So there's a map from S, the S space, locally around S equals 0, to here. Here's holomorphic.
Okay.
Moreover, if you project this down to the T space, then you'll see that in the S space, if you go around this little circle around 0, you end up back where you started. This is analytic.
Yes.
Right? But what happens then when you project down to the T space? You're going around W times because S to the W is T. Right? So the fact that this analytic function exists is the Newton-Puiseux theorem. And if you write down and do the bookkeeping correctly, you can see everything that's going on geometrically. Now, mind you, we are not going to attempt to get this series. Some people do. It's called the power series endgame. We'll mention that, but we won't. And I don't think it's particularly. So the lowest power that appears is interesting. That's tropical information if you're into tropical geometry. But that's for another course. This is not a course in tropical geometry. Yeah, great. Okay, and does that clear things up?
Yes.
Yeah. Any other questions? So the really cool thing is that we can actually this is our 0. This is our C to the S space. So this maps here in a way that kind of does this double cover there. And so it looks like there's no way to draw this disk without it looking like it crosses. But that's a feature of only having 3-dimensional eyes. It really doesn't cross. Okay. So we got this map from this disk here, double covers onto the disk down here. And essentially what we want to do is we want to evaluate an integral around that path in the S variables. I want to go around once. Okay, but we don't have any access to this holomorphic map. But we do have access to analytic continuation via the Helmholtz. So we do get to compute this number and go around, well, W times in the circle down here. Well, that'll go around this once. And as long as we're, keeping sample points along the way, we'll essentially have the data to do like a Riemann sum approximation of an integral. Thing to remember is X star, the place you're converging to, it is the average value of the path xi of t as t is looping around t equals 0, w times. Any other questions? Very flexible day. Today's a great day. Okay, great. So, yeah.
Can Poisson series have negative exponent?
Laurent series can have negative exponents. This Poisson series. Okay, so right, good question. What happens if there's a negative exponent? Give y'all a minute.
You had a pole?
Yeah. So as t gets really, really itty bitty, what does xi of t go?
To infinity.
To infinity. That's right. So if we had solution paths flying off to infinity, because for some wild reason we decided to have a start system of degree higher than our target system, then we would see this in the expansion here. So we would have values of t going to infinity, and we would have paths. But that's not going to happen if you choose the right degree. Right? It is going to happen in our multivariate setting. So there's a distinction between the univariate setting and the multivariate setting. Univariate setting, you already know exactly how many solutions there are. Counted with multiplicity, thank you very much, fundamental theorem of algebra. With multiple variables, if somebody gives you some equations, you will not know how many solutions there are with multiplicity just by looking at those defining equations. Great. Good question. So it's dawned on me that there is a subtle thing that I've alluded to a lot that I haven't made explicit. And that is that so far this whole setting, I've told you, always goes from t equals 1 to 0. And always goes from this total degree start system to the system you want to solve. albeit there might be a funny path using the gamma trick. One might ask, well, okay, so what if I choose this t value and this t value? Okay, so let's call this f hat and g hat. And suppose for some reason I know my d solutions over g hat. Could I do the same process to deform these solutions from g hat to f hat? Well, the answer is yes. You literally just write down exactly the homotopy you would think. Let's call it h hat. And if you wanted, you could use the gamma trick, and that would arc the path from g hat to f. So you could do this. This would be the start system and the target system. And this would be called a straight line homotopy. Straight line indicates that it is linear in t. It does not indicate that it's a straight line here, because you can take gammas and it'll curve the path. But there you're only looking at a real path curving. So as far as the algebra is concerned, this is linear in t, so we call it a straight line homotopy. And the story is the same. The thing you need is that g hat is not in. But now I'm going to start giving this set that we've talked about a lot a name. The exceptional set. Equals. I'm gonna bust this down into two separate parts. First one is d mu, and that means there's a multiple root in the polynomial system above that t value. We had a theorem that said this is a finite set. Union. Yeah, let's call it infinity. We'll just be a little bit loose about this. There's a solution flying off to infinity. For us, this is the exact same thing as the degree is smaller than the generic degree d. Okay, so when the degree drops in the univariate setting, you lose a solution. Where does it go? It has to, there's only one place for it to go, infinity. So for us, right now, the exceptional set has two parts. Places where you have multiple roots, and that's some finite set. And places where you have lost a solution to infinity, that is a set of one t value. You can check that. Any questions? So this is important. So where was this hiding under the rug in my previous lectures, right? Anybody remember where I actually needed to know that you could do this? Otherwise, something I said didn't make any sense. When we do a Cauchy loop around t equals 0, I said, okay, now follow it using homotopy continuation. Well, what are you talking about? I'm not going from t equals 1 to t equals 0. And up until that point, all we did was homotopies from t equals 1 to t equals 0. Now, you could parameterize this circle in a way that that path gets unfolded into something from the parameter going from 1 to 0 or 0 to 1, if you like. And that's how you do this. It's actually exactly what you're doing here. But the important thing to think of is that you can actually do it all on this picture. You don't have to do this reparameterization all the time in your head. You can just think about the fact that you can move through this parameter space and follow the solutions. Okay, great. So if you have a finite set, define its trace as just the sum of all the elements in that finite set. If a polynomial with roots alpha I, possibly some of the alphas are green, its trace is the trace of its solution set. And let's say non-constant. Yes, this is the same trace that you studied for a comprehensive exam in field theory. It's the trace of the field extension of the splitting field. But this is not a course in field theory. So this is just the sum of all the solutions. Now in the literature, you will sometimes see the trace be defined by dividing by the size of the set. So instead of taking the sum, you're taking the average. These only differ by a constant. This is not a meaningful difference in the definition of a trace. The benefit of defining it as an average is you can draw pictures nicely. For example, if I have like 100 paths here, its trace will also be on the blackboard if I take the average. If I don't take the average, trace is 100 times up there, right? So when you see people take averages instead of sums, the reason is because they like pictures. That's the only reason. Okay? My pictures will be of averages. It's sums. It's fine to go back and forth. Nothing I say as a conclusion about the trace is going to differ.
So it's a scaling, you're rescaling.
Yeah, by some uniform number that's not going to change for the whole situation. So let me explain with maybe the comment here. So if we stopped here at some t value, we could look at our solutions and we could take the average at some point. This would be like the trace of h of x of t star. Or this is t star. Okay. And since these paths move continuously, the trace will move continuously. It also gives a path. Let's think for a moment what we think that path might look like. Well, it's a linear function. So just some line. No curviness at all. This is not too hard to prove. Which constant on the board represents the sum of the roots?
D minus C, D minus one.
Yes. Thank you. Negative C D minus 1. Expand this out. How do you get the coefficient of x to the d minus 1? Well, in one of these factors, you pick a root. Everything else gets an x. So you're picking up negative alpha I times x to the d minus 1 for each of your alpha i's. Okay?
Can I find out there's a bi-series?
Say it again.
There is a bi-series.
There's a bi-series?
Minus CD minus 1
Yeah,
bi-series
divided by CD.
divided by CD.
Oh my gosh.
You could just take a univariate guy, but anyway. You could just take
Well, negative CD minus 1. And, F is mock.
one, yeah.
This is monic. Okay.
Yeah, sure.
As long as that fits. Everything's monic. Everything's monic. Okay. Thank you. Absolutely correct. That would have been a mistake of it. Thanks. Okay, so in order to show that this is a linear function of t, all we really have to do is show that the second highest coefficient doesn't have t raised to any power in it. But of course not. Even this doesn't have t raised to any power. Okay, so the trace is linear. That's going to come back in a very, very important way when we study witness sets. Okay. So the first idea for an endgame was actually to use the trace. If we've gotten a bit messy, I will read. These are our paths. We know that locally around t equals 0. Each of these collections of curves coming together belongs to some analytic disk. And so, for example, this one is that, and then there's actually another one corresponding to this transversal curve going through. This one is great. So the idea was stop your homotopy at some epsilon. Make a pretty good guess about which points are going to the same place. That's going to be some heuristic. But maybe I make the guess that this, and this are going to the same place. Well, it's x4, x3, x2, 1, all s functions of. Well, since x2, x3, and x4 are all going to this limit point x star, their trace, when you take the average, will also go to x star. Their average value will go to the same thing. And so there was this idea, okay, well, that's very nice. Maybe the trace of all of the points on this disk will give me a good guess, and I won't have to do one of these quotients. That makes sense? That's it. Well, that is a special case of the Cauchy. Why? What does it mean? So for example, let's take just x2 and x4, for example. We might take the trace, right? And then x3 is kind of an accident right now because it goes through transversely. But if I have my S plane, right, so what am I doing? I'm taking different S values and sampling to get different values around this boundary. And I'm taking their average. Well, if this has winding number W, and I take W equally spaced points, where do they show up here? They are exactly these points. So taking those averages to approximate the Cauchy integral is the same thing as taking the trace. So the reason why you will not hear about any trace endgame is because it is a special case of the Cauchy endgame where you approximate an integral over a path that has cycle type W with W equally spaced points, one of which is at okay, so that's called the trace endgame. We won't do that. And then finally, the last endgame I want to chat about. So we talked about Cauchy endgame, that's state-of-the-art stuff. Trace endgame, totally subsumed by the Cauchy theory. And then finally, there's a power series endgame. So power series endgame tries to get your hands on the agents. And it does this just by interpolating and extrapolating. So you have some curve x of t. Right. And let's say we know W. Okay, let's say we know this cycle number. Well, if I have 2 points, then I can guess where we're going by just drawing the secant line, right? And then my guess at t equals 0 would be there. But if I had 3 points, I can interpolate 3 points by a quadratic polynomial. And I might have a better approximation by evaluating that approximate power series at t equals 0. And I can up that higher and higher. What do you need? You need lots of data points and lots of precision because you're probably at some really, really small t value. All right. Okay. So being able to interpolate and extrapolate in a numerically stable way is the topic of numerical analysis class. If people study these things, they're well understood. In order to play this game, you need to know W. And so you would have to do these loops anyway. And so there have been some comments in the literature where this is kind of like, and it's overkill, you already did the Cauchy endgame essentially to get the winding number. You might as well just approximate using an approximation for the integral, the Cauchy integral. Why bother doing a power series and extrapolate? So those are those are 3 of the endgames for handling solution multiple roots at the end. Questions? So that ends the topics of endgames. No, it doesn't. I want to tell you 2 more things. Okay, so when you do any computation, either by hand or on a computer, it's some series of steps, some calculations you have to do, right? So maybe yeah, maybe we started doing these path trackings by hand in this class. And we had 7 paths we wanted to track. Okay. So I could ask y'all to do that by hand. I'm saying, okay, step size is 0.1. We're going to use the Bezout total degree start system. You know what Newton's method is. You know what Euler's method is. You could do all these computations by hand, right? And if I asked you to do that as fast as possible, and you were allowed to work as a team, what would you do? You would assign to each of you one of the start solutions to do. You would not each try to do all 7. You would give each of you one, and you would finish, ideally, 7 times faster. Although there is variance into our calculation abilities by hand. Okay. So some of us will be a little bit slower because, we're like me, I'm used to just using a computer for everything, so I can't do simple arithmetic anymore. You don't use it, you lose it. Some of us will be able to do this real snappy. And we'll all end up being done at different times. Okay. So that process is called parallelization. When you have a task and you can split it up into several tasks, that's parallelization. And you're saying you're doing the computation in parallel. Now, inside your computer, there are many little computers. Okay, processors, cores, threads. I'm not getting into the distinctions of this. But you think about your computer as your laptop has 4 to 8 to 16 little computers. Okay. Back in the day, you had like 1 or 2. Okay. Now you have 4, 8, 16. When you talk about supercomputers, it's not that the computers are super duper fast, although some are. The real appeal is that there are lots of processors, right? So when you have to do tasks like this, you can do them very fast. Okay, great. So that's what's going on in your computer. And so you can code homotopic continuation in a way where each thread is doing a separate path track. And indeed, this is code in homotopic continuation. And it is very easy to run Julia on multiple threads. Okay, so we'll see that this in the second lecture of the day. Now, I want you to imagine, so Deepak is very, very fast at doing homotopic continuation by hand. Taylor is very, very, very slow. All right, and we're trying to solve this. So Deepak's already over here. Taylor is like really struggling over here. And Deepak looks around, he's like, okay, everybody else is not finished. Like, okay, let me do a Cauchy move. Okay, finds this, which by the way is the one I'm going to, right? And then he comes back, he's like, okay, I got a good approximation of this, but by the way, as a byproduct of me doing this endgame, I found this point. And since the difficult part of homotopic continuation is near the poorly behaved areas and not in the rest, Deepak's like, well, let me speedily meet Taylor this way. So I can tell Taylor, hey, you can stop by your numbers. Yours is also my solution. You're one of the multiplicities. Right. Now you can imagine, like maybe I'm trying to solve some system where there's lots of multiplicity. I have something of like multiplicity 10, right? As long as I got like one really speedy person here, then they can track back everything and tell the other processors to stop and work on something else. Okay, so that's a whole type of parallel endgame called the Cauchy trackback endgame. And a lot of the fun of this field of mathematics is coming up with these clever ways to improve your algorithms, using the fact that this process is inherently really well behaved on multiple threads. Okay, so that's a fun idea. Yeah, now I think I really have finished everything I want to chat about. So that ends our lectures, our Blackboard lectures on univariate homotopy continuation. Pretty much everything in the class until we get to witness sets are variations on this theme. You'll see the same picture over and over again. I apologize for that redundancy. However, it is good to just hammer this picture into your head. It will become slightly more complicated, but not very much. and all of this following loops and going around and getting monodromy, that's all gonna appear again, and it's gonna be great. Okay, ending the recording, and then we'll continue in our next lecture when we compute singular solutions at the end using the Cauchy endgame.